Space-time transformations of the ordered vacuum. Every model of space-time behavior transforms in a certain way as the frame of reference changes. The frame of reference can change location in space or in time. The resulting transformation is called a translation. It can change orientation, in which case the resulting transformation is called a rotation. But what we are most interested in here are changes in motion. We want to know how the model transforms when a test particle is seen by observers moving at different speeds. This is the space-time transformation referred to in the title. Newton's laws of mechanics transform according to what is known as the Galilean transformation. Electromagnetic phenomena transform according to the Lorentz transformation. Einstein showed how to view the world so that everything would conform to the Lorentz transformation. All of modern physics, including the Standard Model, of course, is based on the Lorentz transformation. In this lecture, the space-time transformation that the ordered vacuum model conforms to is determined. If it conforms to the Lorentz transformation, all is well. If not, the model would have to be revised or discarded. Consider a test particle and two observers, one traveling with the particle and one moving at speed v relative to the particle. For an observer at rest in the particle's rest frame, the particle appears to be jumping around at the Zitterwagen frequency, executing an unbiased random walk. The observer would have to see the particle encountering the same number of vacuum exchange scattering events in any given direction as in the opposite direction. Now, nothing is gained by doing a full three-dimensional version of this derivation. There is no loss in generality by confining the derivation to one spatial dimension. So a one-dimensional version is presented here. Therefore, left and right will be used as the two possible directions along this dimension. An observer moving to the left with uniform speed would see the particle moving to the right. This observer would have to see more vacuum exchange scattering events moving the particle to the right than to the left to account for the particle's motion. Thus, the two observers would disagree on the right-left status of some subset of vacuum exchange scattering events. To reconcile this, what is sought is a linear transformation between time and the coordinate in the direction of the motion, taken to be the x direction, which accounts successfully for the velocity, averaged over a large number of vacuum exchange scattering events, in both the particle's inertial rest frame and the other inertial reference frame moving with uniform velocity v in the x direction. In order to approach this mathematically, consider the coordinate vectors x1 through xn of the n points to which vacuum exchange scattering brings the particle in time delta t equal to tn minus t1 in its rest frame. In this, t1 is the clock time that the particle is at x1, and tn is the clock time that it is at position xn. The total distance covered can be written as delta x equals the magnitude of the difference vector between the vector xn and the vector x1. We can make similar definitions in the moving prime frame so that delta x prime and delta t prime can be written for the moving frame. Notice that we allow the times to differ, but require the number of events to be the same in both reference frames. These frames can be related with the linear transformation L shown here. L is the matrix whose elements are L11, L12, etc. that relate the prime to the unprimed frame of reference, that is, the rest frame to the moving frame. This is a space-time transformation. Since the unprimed frame is being considered as the rest frame, then it must be that delta x can be made to be arbitrarily small for n sufficiently large, so that the matrix multiplication gives delta x prime equal to L12 delta t and delta t prime equals L22 delta t. The delta x terms are zeroed out since delta x can be made to be arbitrarily small. In the moving primed frame, the particle speed must be v equals minus delta x prime over delta t prime, so that dividing these equations, the one for delta x prime and the one for delta t prime, gives L12 equals minus V times L22. With the definition, gamma defined to be the ratio of delta t prime to delta t, which you will need to remember for later, it follows that L22 equals gamma from the equation delta t prime equals L22 delta t. Also, L12 is minus V gamma. The transformation matrix now takes the form shown, with the right column determined and the left column still to be determined. As is standard in derivations of spacetime transformations, the common sense notion that the inverse transformation is the forward transformation with V replaced by minus V is used. This allows us to actually form the matrices L of V and L of minus V, and the product L inverse times L, which is equal to L of minus V times L of V, and set it equal to the identity matrix I, and solve the resulting equations. The result is that we find that L11 is equal to gamma, and L21 of minus V is as shown. Hence, the transformation matrix takes the following form. Notice that V has been replaced by minus V in the 2-1 element. Also notice that the diagonal elements are equal to each other. Well, now that we have determined the form for L, we must obtain a functional form for gamma of V. It is also standard in derivations of spacetime transformations to invoke the notion of closure. This involves replacing successive transformations with a single one. For example, consider two transformations L1 and L2 associated with velocities v1 and v2 respectively. There is a transformation L associated with velocity v that is equivalent to the product L1, L2. But we have just seen that the transformation matrix generally has the diagonal elements equal to each other. So, if we form the product L1, L2 equal to L of v1 times L of v2 and equate the diagonal elements, we get the equation shown here. Dividing both sides by v1, v2, gamma v1, gamma v2 gives this equation, where the variables are separated. That is, the left-hand side depends only on v2, while the right-hand side depends only on v1. Since the variables are now separated, and v1 and v2 are independent of each other, the functional form on the left and the right must be constant functions of v. For later convenience, we will call the constant 1 over c squared, where c, which has units of velocity, is not yet to be identified with the speed of light. If gamma is an even function of v, that is, if gamma of minus v equals gamma of v, then this equation is easily solved for gamma of v. But in addition to this solution, there are two more solutions that do not have such symmetry. As it turns out, the only way to preserve the norms of spacetime vectors under these transformations, thereby guaranteeing the constancy of rest mass, for example, is for L to have unit determinant. Now, since determinant of L is equal to the ratio of gamma of v to gamma of minus v, this can only happen for the even solution, gamma of minus v equal gamma of v, thereby ruling out the other two solutions. The transformation matrix can now be written in its final form, shown here, with gamma taking its usual form. But we are not yet finished, since we haven't yet argued that c is the speed of light. To make such a case, first, notice that if v is greater than c, then gamma is imaginary. Recalling its definition, an imaginary gamma would transform real time into imaginary time, and nobody knows what that would mean. So we must consider c to be a limiting velocity, a velocity that nothing could exceed, to keep gamma real. Of course, This model already has a limiting velocity built in. If all the steps of a particle's random walk are in the same direction, then it can go no faster, and it is going at the speed of light. Thus our case is made. We are justified in equating the constant c, obtained from the separation of variables, with the speed of light. Thus, the set of ideas that we have put forth in this work regarding the nature of particles and how they interact with the ordered vacuum is sufficient to uniquely determine the Lorentz transformation as the only spacetime transformation that is compatible with these ideas. Indeed, we have shown here that the Lorentz transformation is precisely what is needed to enforce the proposition that vacuum exchange scattering is able to account for the particle's motion in any and all inertial reference frames, and therefore that all motion can be regarded as based on vacuum exchange scattering in an ordered vacuum. Thank you for listening.